What's up, Fortnite gamers? Mr. Cully coming at you, and today I got another video for you. Thanks for subscribing, by the way. And we're going to be talking about the study guide that I assigned to you on Monday that is going to be due tomorrow, aka Thursday. So we are going to have a review day tomorrow, but I wanted to make sure that we're all on the same page as far as what the answers are on the study guide. I'm not giving you every single one, but I'm going to give you most of them. So if you're watching this, you're rewarded. You get to know the answers. If not, then just make sure that you have it done. So let's go ahead, and I'm going to go over some of the ones that we went over yesterday too to make sure that we're on the same page. Let's go ahead and get started. So what determines the chemical properties of an element? So chemical properties, that's things such as how they bond or what they do, how they react with other substances, such as, you remember the first column on this periodic table, the alkali metals, they all have something in common. They all have one valence electron, and they all explode when they hit when they hit water. I get excited, except for hydrogen. So they have a similar chemical property in the fact that they have that one valence electron. They all explode when they hit water. Same thing with these guys over here on the very right-hand side, the noble gases. They're all very unreactive. Why? They have a full shell of outer electrons. They are content with what they have. These guys over here, these are super reactive, but they're nonmetals. What makes them super reactive? They have 7 valence electrons. So what determines the chemical properties of an element? It's the number of valence electrons that element has. So number of valence electrons would be your answer. For example, we just said everything in that first column has one valence electron. They all have similar chemical properties because they all react violently with water. So, and same thing over here, 8 valence electrons, they all have a full shell, they don't react at all. So it's the number of valence electrons that determines the chemical properties. All right, what do Lewis dot diagrams help us visualize? Well, Lewis dot diagram is something like this, where you got sodium, for example, and you got chlorine, and you draw these dots around it. What do those dots represent? Valence electrons, the electrons in its outermost shell. So what does it help us visualize? It helps us visualize the electrons around it, and it helps us visualize bonding. So here, for example, we draw an arrow from sodium to chlorine to show that sodium is giving up its electron to chlorine. So it helps us visualize the valence electrons and helps us visualize bonding. Okay, so it's super helpful with that. If we didn't do this, we'd be drawing out the entire atom with every single electron. We don't want to do that. We just want to stick to the valence electrons because those are the ones that are used in bonding. All right, what happens to electrons in ionic bonding? Well, I gave this example up here where we see that sodium, which is a metal, and chlorine a nonmetal. What's happening to that electron? That is being transferred, okay? Those electrons get transferred. So I'll say electrons get transferred, which means it's either given or taken from a different element. So ionic bonding, the electrons are always transferred, given or taken. All right, when an atom loses an electron, what charge will it have? Well, think about it. An electron is a negative thing. If it's losing a negative thing, what's it going to be? More positive or more negative? It's going to be more positive. Kind of like if you get something negative out of your life, then you become a more positive person. So if you lose something negative, you become more positive. Well, what if you gain something negative? What if you gained an electron? Then you become more negative. All right, it's kind of the opposite of what you think. Why do you think ionic bonding has the word ion in it? Well, ionic bonding is going to have ions in it. So if we're looking at ionic bond between sodium and chlorine, these are both ions. They're going to attract each other because sodium gave up its electron to chlorine. So ionic bonding is just bonding between two ions. So bonding between ions is ionic bonding. That's different than covalent bonding where there's not ions involved. Here, there's ions involved. Well, what's an ion? An ion is a charged atom. Don't overthink it. Ionic bonding is bonding with ions. All right. Anions and cations, I'm going to let you guys figure that out. Why do cations and anions attract each other? Well, this one's pretty easy. Opposites attract. I like drawing the smiley face. They attract each other. Opposites attract. Cute face. Oh, yeah. What does that look like? Looks like Justin. I'm bad at Rocket League. Yep, perfect. All right, Lewis dot structure method. So here we're given ionic compounds and we want to use the Lewis dot structure method. What do we do there? Okay, well, Lewis dot structures, that's where you draw the dots. So lithium and fluorine. Lithium, if you want to see how many dots it has, you got to go back to your periodic table, which is here. Make sure that you have this. This is golden. Lithium has 1 valence electron and fluorine's got 7. Okay, so now I go back here. Lithium has 1. Fluorine's got 7. Well, this is ionic bonding, so I know that that electron is going to be transferred. It's going to be given to fluorine. So what do? I draw an arrow from that electron to the open spot on fluorine, okay? Fluorine's filled at the top, the right, the bottom, but it's got this empty spot on the left. So that's where it's being drawn to. So now what I do is I look at this. I say, okay, how many lithium atoms did I need to satisfy or to fill fluorine's shell? And I just had 1 of each. So my chemical compound is just LiF. I could put Li1F1, but I don't really need to. It's just implied. Last thing, name the compound. Okay, I need to name the compound. This is just lithium fluoride. Why is it just lithium fluoride? Because it's not covalent, so I don't use prefixes. All right, we'll skip 10. We'll do 11 because that one is one of the tougher ones. We got aluminum and we got oxygen. So got to find out how many dots, how many valence electrons each one has. Aluminum is right here. It's got 3 valence electrons, and oxygen's got 6 valence electrons. So let's go ahead and draw that. Aluminum's got 3. Oxygen has 6. I did that wrong. There we go. So I know that aluminum is going to donate because it's the cation. It's going to lose electrons. So those 2 can go in the 2 empty spots on oxygen. But here's the problem. I've got 1 left on aluminum. So what do? I have to add another oxygen. Why? Because I need more spots to fill. I need more spots to fill, so I have to add another oxygen atom. So now I've got 2 more spots to fill. So that electron can go in one of those spots. But now I have another problem. I've got this empty spot that I need to fill. So I need to add another aluminum. It's this game of keep adding until it works out perfectly. So now I've got this 1 spot to fill on oxygen. That one from the next aluminum can go up there. Okay, now I have a problem again. I've got 2 extra to give from this aluminum, so I need to add another oxygen. And this time it's going to work out perfect because this oxygen is going to have two spots to fill, and I've got 2 left from aluminum. So bada bang, bada boom, everything has a place to go. Okay, all the valence electrons are filled. So now I look at this and I say, okay, what's my chemical formula going to be? Well, I had to use 2 aluminum and 3 oxygen. So this would be Al2O3. And what's the name for that? Because it's ionic, there's no prefixes, so it's just aluminum oxide. All right. Crisscross method. So this is where we're using the charges. We use the charges here. So lithium and oxygen, we're looking at their charges. So we need to go back to our periodic table. And lithium is right here. It's got a charge of +1. Oxygen's over here. It's got a charge of -2. So I'm going to write that down. Lithium has a charge of +1. Oxygen has a charge of -2. There's a couple ways to think about this, all right? I can think about it in the sense of I need to cancel out my charges. So these guys need to balance. So I need to keep adding atoms, or ions, until this finally works. For example, I need to add another lithium or I need to add another oxygen until these charges cancel. Because right now, if I were to add up these charges, +1 and -2 add to get -1. Okay? That's not 0. That's not canceling out. So how am I going to get these to cancel? I need to add another lithium. So now if I were to add up all the charges, 1 plus 1 is 2, minus 2 is 0. Now they all cancel. So what my formula be? It'd be I needed 2 lithium and 1 oxygen. It's Li2O. Okay? Or you could do the crisscross method, which is you draw the compound below. This number, this 2, it moves down to here. And this 1 gets moved down to here. It swaps numbers. It swaps places, and it goes down this time as a subscript. You don't carry the charge with it, okay? It's just a little trick. That's all it is. So you still get the right answer if you swap these numbers. So Li2O1, but remember, you don't need to write that 1, okay? It's implied. So Li2O. And the last thing, you need to name it. So this would be lithium oxide. Okay. And you can use that same method for 13 and 14. All right. Ionic compounds form 3D structures called crystal lattices. Okay, and crystal lattices. What does this look like? Well, if you think about a lattice, maybe you guys have a deck, and underneath that deck, you've got this thing called a lattice. It kind of looks like this grid, this checkered looking thing. What does that look like? Well, a 3D structure that's a lattice is going to look something like this. You're going to have this every other pattern going on of charges, okay? And so if I'm drawing, it kind of looks like this. All right, and then it kind of like is like a 3D looking thing where you get, I'm so good at drawing. You know what I'm saying? Look at that, that's beautiful. It's like a cube, okay? It's got this every other pattern going on. So ionic compounds are made of ions, right? Which means they're made of positive and negative charges. So every positive charge is going to surround itself with a negative charge and vice versa. They're all interconnected. Looks something like this. Okay. Because of that, it creates a very rigid structure. We compare this to a jungle gym. Because if you think about jungle gym, there's interconnected bars everywhere. It's very hard to break apart a jungle gym. Why is that? Because there's so many interconnected parts that it's not just one bar that's holding on for dear life. It's connected to many different points. So because of that, it's got a very rigid and strong structure. So the next question, based on their structure, why might ionic compounds have high melting points? Like we watched that video on melting salt. Why does it take such a high temperature to melt salt? It's because of this structure right here. It's very, very rigid. I don't know if I spelled that right. And strong. Okay? It's very hard to break those bonds. It is hard to break those bonds. It is hard to break those bonds. It takes a lot of energy, because it takes heat, okay? You need a lot of heat to break those bonds apart to make that structure start to flow. All right, draw a diagram that shows why ionic compounds are brittle. So this kind of goes back to the notes as well. Why is it brittle? Well, think about it this way. If we're looking at our lattice, and we're just looking at a piece of the crystal, kind of looks like this. We got this every other charge going on. But let's say that we hit this thing with a hammer, okay? Can I draw a hammer? It's a nice mallet. Boom, okay? We're hitting this thing, we're hitting this crystal with a hammer. What that does, it's going to shift down. It's going to shift down this entire column of charges. And this is a huge simplification. But if we shift this column down, let's see what happens. We're going to have a minus, a plus, and a minus, and a minus. Am I doing this right? No. We're going to have a plus, a minus, and a plus, and a minus, and a plus, and a minus. Okay. So what I did was we basically take a hammer, hit this column down, okay? Because brittle means like it's going to break easy. It's going to shatter. So this hammer hits the crystal. It makes this this column shift downward. So what does that do? Now we go from every charge is surrounded by its opposite, to now the positives are by the positives and the negatives are by the negatives. Well, what do we know about like charges, similar charges? They repel each other, right? The positive ends, like if you ever had a magnet where you put the same ends together, it repels. So what does that do? It creates a crack, all right? A crack right there. So now this crystal breaks apart, okay? AKA, it makes it really brittle. It's easily broken, okay? So when you hit a crystal, AKA an ionic compound, it shatters easy because you're disrupting that every other charge kind of thing going on in the structure. It makes it so that the charges are no longer aligned anymore, and it breaks. So that's why they're brittle. That's different than melting it. Melting it is saying, okay, you're breaking every single bond within it. You're not breaking every single bond in here. You're just you're creating a crack. Melting something involves so much energy because you have to break every single bond that's connecting this entire lattice. All right. Why can't ionic compounds conduct electricity when they're solid, but can when they're molten or dissolved? Well, going back, I'll just kind of go back to this. These charges, we said, are very rigid. They're stuck in position, kind of like a jungle gym. Okay, you can't really move things around in a jungle gym because it's so interconnected. So charges need to be able to flow in order to conduct electricity. You need flow to conduct electricity. Because the charges in a solid cannot flow, they're not able to conduct electricity. But let's say that you were to melt this down. Let's say that you were able to melt this down. Okay. Now these charges are just flowing around. All right. You got boom, bada bang. They're not really kind of next to each other anymore. And they're able to flow. You think about a liquid. If this is on a liquid state, they're able to flow. Because of that, because they're able to flow in a liquid state, they're able to carry charges from one place to another, essentially. So when you think about something being molten, you think of it as a liquid. You think about something being dissolved, you think of it inside of a liquid. All right. These two create flow of charges. When it's a solid, there's no flow. No flow of charges. It's too stuck in position. Those charges can't flow. But when they're molten dissolved, yes, they're able to move around and they're able to flow. That's the best way I can describe it. All right, what is the octet rule? You know that. Why are hydrogen and helium fine with only 2 valence electrons? So hydrogen and helium are the 2 smallest elements on the periodic table by mass. You got hydrogen here and helium here. Hydrogen normally only has 1 electron at all. Helium usually only has 2 electrons at all. So if you remember, if you're drawing the Bohr model, that's the nucleus, the first ring can only hold how many? 2, okay? So technically, hydrogen does have a full shell with only 2 valence electrons. Same thing with helium. They're content with 2 because that first shell can only hold 2. Every shell after that we kind of talk about will have 8. So they're fine with 2 because their full shell is only 2. What are the 7 diatomic molecules? What did I say I was going to name my baby? Hofbrinkel. Hofbrinkel. Okay. So these are all diatomic molecules. What's diatomic mean? What does the prefix di mean? 2. What's atomic mean? Atoms. So these guys exist in pairs. So hydrogen, the H, is H2. Okay, that's hydrogen. Hydrogen gas that we breathe in is actually H2. It's bonded to itself. Oxygen gas that we breathe in is O2. Fluorine is F2. Br, bromine, Br2. I2, N, N2, and Cl, Cl2. All of these atoms, when they're alone, cannot exist alone naturally. They have to bond to themselves. So we call them diatomic molecules. All right, here we go. So we got compare and contrast ionic and covalent bonding. Bonds are shown with lines. All right, lines is going to be covalent because that's sharing. Bonds are shown with arrows. That's transferring, so that's going to be ionic bonding. Prefixes are used in naming. Prefixes are used in naming with covalent bonding. No prefixes are used in naming. That would be ionic. We don't use prefixes with ionic bonding. The last element ends in "ide." Some of you would put ionic bonding, and you'd be right. But in covalent bonding, the second element also ends in "ide," so this would be both. Both elements form an octet. What's the point of bonding at all for elements to form an octet? These are both bonding. They achieve their octet in different ways. They achieve their octet with ionic bonding by transferring the electrons. They achieve it with covalent bonding by sharing electrons. So this one is both. Form between a metal and a nonmetal. If it contains a metal, that's ionic bonding. Form between two nonmetals, that would be covalent bonding. So the secret code to my house is 247561138. You're not going to get much. All right, fill out the prefix chart. This one's in your notes. Okay, look this one up. And then drawing the Lewis structures. So we've kind of beaten a dead horse here. Draw the Lewis structures and name each covalent compound. So let's just take a look at this one. H2S, you have to draw out the dots. So we got two H's. Let's draw them like this. Each one has one valence electron. And then you got sulfur, which has 6. Now the question is, what do you do? Well, sulfur's got 2 lonely sides to the left and to the bottom. And these hydrogen have 1 lonely side. So you just connect them like this. And now sulfur's happy and each hydrogen's happy. How do I name this? All right. So this is covalent. It's covalent, so I need prefixes. So my first one is hydrogen. So it's going to be hydrogen. And my last one is sulfur, so it's going to be sulfide. I totally spelled that wrong. Sulfide. But now I need to go back and add the prefixes. Well, 2 would be di. So it'd be dihydrogen because I have 2 hydrogen. And I've got 1 S. What's the prefix for 1? Mono. Monosulfide. So this is dihydrogen monosulfide. All right, let's do another. Let's do one more. Let's do CCl4. So carbon's our central atom because I bolded it. Carbon's got 4 valence electrons, like so. And it's got also 4 chlorine. Well, I can already kind of recognize that chlorine's going to bond to the carbon on each side. So I'm going to surround my carbon with my 4 chlorine, make it nice and symmetrical. And each chlorine's going to have 7 valence electrons. So I'm going to draw my 7 dots, but I'm going to face my lonely side of each chlorine towards my carbon. You see what I'm doing here? The lonely side is going to be facing towards my carbon because it's going to make it look a lot cleaner. All right, and so all I do now is I'm going to connect my lonely sides because chlorine has 3 good sides. It's got 1 lonely side. Carbon's got 4 lonely sides, so it's going to form 4 different bonds. So all I do is I connect these dots. These guys are going to share their electrons with chlorine. And it looks like this. Now everybody's happy. Carbon gets its 8 from these 4 lines. Remember, each line represents 2 valence electrons. So how do I name this? All right, well, it's covalent, so I need to use prefixes. But before I do that, let's just write the base of it. I've got carbon. And I got chlorine, so this would be chloride. Now I'm going to go back and add prefixes. Well, because the first element in the compound only has 1, okay, there's only 1 carbon, I do not need to write mono. That's one exception. You do not write mono if the first element in the compound only has 1. So I'm skipping the prefix here, but I do need to add the prefix here. Chlorine's got 4. There's 4 chlorine. So what's the prefix for 4? It's tetra. Okay, tetra. So this is just carbon tetrachloride because I've got 1 carbon and 4, aka tetrachlorine. All right. That's all I'm going to do. If you guys have any questions or any specific ones that you want me to go over, please reach out and I'll be sure to help you. But we're just going to do a review tomorrow and kind of move on and do the test. All right. Guys, have a wonderful day.